Let's take a look at an example problem for how to solve a system of equations where not both of them are linear. So here this tells us to graph the system, tell how many solutions there are, and estimate the solutions. In this case, since we are told to actually make an estimate of what the solutions are, we will have to make a good graph of this, looking for actual ordered pairs, and it can't just be a sketch, a rough sketch. However, if we were just told to tell how many solutions there are, it's a good possibility that we would be able to do so by just making a rough sketch of the graph, because we may know what each of these graphs look like, and since we know what they look like in this case, we would be able to tell how many times they will intersect. Remember, solutions to systems of equations are places where the two graphs intersect. So let's go ahead and start off by just making a rough sketch of this system on the same set of axes. We know that y equals 2x squared is a direct variation equation, and since its exponent is 2, we know that it will look like a parabola. So it'll be centered here at the origin, or it'll have a vertex here at the origin, and it will look like a parabola, about like this. And we also know that the second equation is a linear equation. There's no exponent on the variable, and the variable is not in a denominator. So this is a linear equation. Its y-intercept is 1, so it will touch the y-axis right about here at 1. And its slope is 1. We could imagine this coefficient of x to be 1 here. So the slope, which is the coefficient of x, is 1, so it'll rise 1 and run 1. It'll come up at about a 45-degree angle and go through that point. Now, we're looking for the set of ordered pairs, x and y, that satisfy both of these equations, which lie on both of these graphs. If they satisfy both of these equations, the x and y coordinates will lie on both of these graphs. So we're looking for the points where they intersect. It appears that they will intersect in two places. The line and the parabola intersect here and here. So right now we could probably answer this question about how many solutions that there are. Based on what we know about the shapes of the graph, we think that there are probably 2 solutions. In order to estimate the solutions, however, we'll have to make a more exact graph. So let's do that now. We'll make a couple of xy tables. One for the parabola, y equals 2x squared, and one for the line, y equals x plus 1. And when we graph this, we'll go ahead and try to get a snapshot of what's going on in the negative and the positive. Now this picture actually helps us determine what x coordinates might be good to use. It looks like there will probably be a solution in the negatives of x and in the positives. So let's go ahead and pick -2, -1, 0, 1, and 2. Over here we will square -2 first. This is going to be 2 times whatever the x is squared. The x here is -2. The order of operations tells us we have to square before we multiply. -2 squared is +4. Then we have to double that times 2, which will give us 8. So again, here we're going to square first, then multiply by 2. -1 squared is 1, times 2 is 2. 0 squared is 0. 0 times 2 is 0. 1 squared is 1, and 1 times 2 is 2. And 2 squared is 4, and 4 times 2 is 8. So here are 5 ordered pairs, -2, 8, -1, 2, 0, 0, 1, 2, and 2, 8. These are 5 ordered pairs that lie on the parabola here. Now let's find 5 ordered pairs that lie on the line. Here we're just going to take our x-coordinate and add 1. So when we add 1 to -2, we'll arrive at -1. -1 plus 1 is 0. 0 plus 1 is 1. 1 plus 1 is 2. And 2 plus 1 is 3. Now we can graph each of these points on the same set of axes. So we'll set up here an x and a y axis. And I will go ahead and graph this first equation in green. So I'll graph -2, 8, 1, 2, 3, 4, 5, 6, 7, 8. -1 on the x and 2 on the y. Then we're at 0, 0, 1, 2, and 2, 8. And I'll try to make as smooth of a curve as possible as I connect these points, because the more accurate I am with the graph, the closer that I will be able to find my solutions. So that's roughly what the parabola should look like. And if we look at the rough sketch, it looks like we did a nice job with that as well. Now we'll graph the line in blue. It looks like we lost some of it here. It's y equals x plus 1. And we'll graph that in blue. So we have an x-coordinate of -2 when y is -1, so we'll go to the left 2 and down 1. And -1, 0. And we're going to keep going. Now another way we could look at this is the slope is 1 over 1, so I know my line's going to look like this. And since this is a line, I'm going to go ahead and use a straight edge to connect these points so that this is as accurate as possible. And again, we can tell that this actually graphed equation, where we actually went through and found more exact type values, looks a lot like our rough sketch. And indeed, we do notice that there are 2 places, one right here and one right here, where our 2 graphs intersect. That means that there are 2 solutions to this equation. There's 2 points, x and y, that will be able to be plugged into each of these equations that will make them true. Now, if we would have looked at our tables here that we made, we would have been able to have predicted one of them already. Take a look at the table and see if you can figure out how you would have known that there is already an ordered pair x and y that satisfies both equations. If you look here, we find the point when x is 1 and y is 2 to satisfy the first equation, and we also find the point when x is 1 and y is 2 to satisfy the second equation. That implies that this point works in both equations, therefore it is a solution. Our graph confirms that. When we go to the right 1 and up 2, we are at the point 1, 2. This is a solution to our equation. It appears that the other solution does not lie right on a grid line, so we will have to estimate the coordinates of that point. It appears that to find the other point where the 2 lines intersect, we will have to go to the left by about a half and up by about a half. So the coordinates of that point, when we go to the left a half, would be -1/2, And when we go up by a half, we'd be positive 1/2 on the y, which would leave us an x-coordinate of negative 1/2 and a y-coordinate of positive 1/2. So we can tell that these two graphs intersect in two places, so there will be two solutions to this system of equations. Just like we list solutions to one equation in set brackets, we also list solutions to systems in set brackets. In this case, there is more than one solution to this system of equations. Remember, when you find solutions to systems of equations, you are not just finding a single variable, because there are two variables involved in the system, an x and a y. So we have to list the variables as ordered pairs to show that we found both an x and a y. One of the solutions has an x-coordinate of negative 1/2 and a y-coordinate of 1/2. So one solution that will make both of these equations true would be if I substitute in negative 1/2 for the x and 1/2 for the y. That should work in both of these equations. The other point that would satisfy both of these equations would be the point 1 on the x and 2 on the y. Now you could substitute these coordinates into each of these equations and simplify and find that you will find a true equation results. Remember, whenever you solve a system of linear equations or a system of any equations, you are looking for all of the variables. In these cases, x and y. You're going to have two variables, two coordinates in each solution. If you're going to actually estimate the solutions, you need to have a fairly precise graph where you have found some coordinates using an xy table and connected them either with a smooth curve in the case of a parabola or with a straight line in the case of a linear equation. You need to be fairly precise if you're going to actually estimate these solutions. However, if you're just looking for how many solutions there will be, oftentimes you can tell by simply making a quick sketch of the graph if you are confident in the shapes of the graphs. In this case, we had a fairly high degree of confidence that we had two solutions because our parabola and our line should have intersected twice. And sure enough, they did. Now, we had to do a little bit of estimating to find this solution. We are not certain that this is actually negative 1/2, 1/2. It could be something very close to it. And this is one disadvantage of using graphing to solve systems of equations. There are other more powerful algebraic methods to solve systems that will always give exact solutions. Graphing is nice to see a visual representation of where the x's and the y's will be the same, but it doesn't always yield exact solutions.